Well, good morning, everyone. As far as our mechatronics subject has been considered, we are in the topic of transistors. Always, we have been discussed regarding the transistors in the previous class, and in the present day's class, the combination of transistors leads to an junction, and the junction field affect transistor, its characteristics, construction, behavior, and the purpose, main aim, and scope will be discussed in the present day's class in detail. The basic principles related to the field effect transistor. These are the devices in which the current is controlled by the application of electrical field, the action or application of electrical field rather than the injection. So we having a little bit of clarity that combination of diodes, either PN or NPN diodes, leads to sandwiching of diodes leads to the transistors, and sandwiching of these transistors related to the field effect transistors, right? Junction, and the meeting of two different transistors leads to a junction, formation of a junction. It's called junction field effect transistors. And what are the different variations that are being taken place when the terminals has been connected at different regions? As far as the previous class has been considered, we have a look at these transistors that we are having three different terminals, that is emitter, base, and collector, and the same terminals will be existing in the case of this field effect transistor also, but 3 plus 3, and sandwiching of one of the terminal will be taking place and leads to a nominal change in the nomenclatures related to the terminals. Here, in the case of this FETS, there is field effect transistors, we'll be naming it as the source, gate, and a drain, where it will be considered as per the directional basis, that is forward bias, P type, and reverse biased, that is N type. And in this, as per the transistor single alone has been considered, we are calling or the nomenclature related to the transistors or emitter, base, and collector. In the case of this FETs, we are having the same nomenclature, that is source, gate, and drain. And moving on with respect to this field effect transistors, these are a weak electrical signals coming between one electrode and creates an electrical field to the rest of the transistors, and it itself selfly creates the electrical field and generates the uniformity of electricity, which is known as unipolar transistor. Unipolar transistor. This is the term to the fact that current is transported by carriers of one polarity. There is majority in the case of polarity, only one polarity, utilizing of one polarity. In the conventional basis, bipolar transistors carry both the polarities also, that is consisting of both majority charge carriers as well as, so hence it has been termed as an unipolar transistor. In the case of these field effect transistors, the FETS family has been considered, it has been divided into the following groups. There is junction field effect transistor, depletion mode of MOSFET. Here, MOSFET abbreviation differs here. Metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. And furtherly, beyond that, enhancement mode of MOSFET also has been came into the one of the classification. So let's have a detailed discussion related to these kinds. As far as our syllabus has been considered, we are having the concept of these junction field effect transistors. So the symbolic representation of these transistors JFETs or here displays. There is the P type when the gate, this is the gate terminal, source, gate and a drain. And as if in the transistor, normal transistor, we have been verified that the nomenclature is related to these three different terminals as differs, that this emitter, base and collector. In the case of a transistor, we have been seen. In the case of these FETs, in the P-type characteristics, we are nomenclating it as an source, gate and a drain. Simultaneously, the symbolic representation for N-type representation, that is, the gate has been indicated initially, and in the case of a reverse strategy, it has been specified. It consists of a piece of high resistivity semiconductor material, usually generally following silicon, and why the silicon has been replaced from the germanium. We have had an initial class discussion. In the initial class discussion, it constitutes of a channel for majority of the charge carrier flows. This is a channel which is conducting the semiconductor channel between two ohmic contacts, this source and the drain. So here, when the diagrammatically it clearly specifies that two p-type positive ions has been trading, and n-type channel which is acting as an for both source and drain as specified here. And this positive P, that is the holes or acting as the gate, and hence it is the basic structural diagram for this junction field effect transistors. And the connectivity of when it has been connected with respect to the metal, what we are calling metal oxide semiconductor field effect transistors, so in the case of MOSFET, shortcut is a MOSFET. This is the channel type, p-type substrates, and then metal has been given into an channel force, and how the free electrons are moving depending upon the negative carriers, and the positive that the gate has been given with respect to the electrical field. Considering the magnitude of this current, it is controlled by an applied gate, as we have been discussed presently, that magnitude and direction of this current controlled by an voltage applied at the gate terminal, which is always in reverse biased, which is always will be in a reverse biased condition. The basic fundamental difference between these BJT, as we have discussed in the previous class, and this JFET is when the JFET junction is reverse biased, the gate current is practically zero. In the case of this bipolar junction transistor, the forward conditions also will be executing, and its characteristics can be layered with respect to the incrementing of the voltage and current characteristics. Simultaneously, in the negative region also will be specified in the similar characteristics as negative incrementing, depending upon incrementing of an current and its voltage factors. But in the case of these junction field effect transistors, when it is reverse biased, the gate condition is practically it is at zero. That the base current of the bipolar junction transistor is always having some of the value which is greater than zero. Either it may be of a unity value or a hope value or incrementing in the case of that current value, right? It's having a high input resistance and high input resistance device when comparatively when BJT is very much low. If the channel in the case of this BJT N type, the middle strategy that is PNP forward mode of BJT, N type is lightly doped and P type initially there is emitter base collector. Emitter is lightly doped, moderately doped P type, and another that is collector base, and next collector is heavily doped. But in the case of this JFETs, the channel is doped with an donor impurity N-type material, which is shows in the diagrammatical, that is pictorial representation. This N-type material is formed and the channel current will consist of the electrons. So overall this will be drain, source, connectivity of this N channel will be having the electrons. If that particular channel is doped with an acceptor impurity, then the p-type material will be formed and the channel current will consist of the holes. Simultaneously, if this channel has been doped with respect to an acceptor impurity, simultaneously acceptors are nothing but the holes and hence these p-type ions, and n-type are the electrons and p-type holes. If this particularly presently existing channel has been doped with respect to the acceptor impurity, then this p-type material will be formed and channel current will consist of the holes instead of these electrons. The n-channel devices have the greater conductivity than the p-type channels. So hence, it is there is a practical condition, that is the electrons which are heavy, very much greater when in the case of n channel over the p channel. Thus, these JFETs are approximately twice as efficient of the conductors compared to the p channel counters. Hence, this moderately this n channel will be acting with respect to a donor impurity. Right. Moving on to the basic structure of this JFETs, there is a so far discussed related to them working characteristics and what are the basic concepts need to be done, or in what way the doping conditions will be maintained for the different gates, and its performance criteria has been discussed so far. And moving on to the basic structure of the junction field effective transistors. As a symbolic representation have been seen earlier, it contains the ohmic contacts, that source and drain. It conducts the current equally well in either of the directions, as the source and drain leads are usually interchangeable. Even the source and drain has been interchanged from source to the drain and drain to the source. Commonly, the current will be getting conducted. So that's the case in the pictorial representation. The pictorial representation also specifies that, because why? Because here always the source and the drain are being acting with the same channel reference, that is an n channel reference, and almost it is having the donor impurity itself. When that electrons that exhibits from the n channel towards the p channel, that is acceptors, the EMF will be getting generated, and hence the quiet this current will be producing when these electrons has been cascaded with respect to the holes. This is the basic structure: source, gate, drain. Here the primitive role plays with respect to this circuit diagram, and the common terminology is utilized with respect to the N type and P type. We will have a just look. JFETs with N channel, there are two positive regions which are electrically connected from the gate. Here is positive 1 and positive 2, and in the case of this B, commonly connected, it is commonly connected, simplified, with more across the sketch of the cross section, practically N channel JFET, right? So commonly connected is a source and a drain has been represented in the case of this diagram, which is increase, which just passes with respect to P type and N type, and hence the depletion layer which is being specified in respect to the cascading. Here it is in P type and N type, and this is the depletion layer acting between these diode, or P, N, and next P, and this is the depletion layer in between this N and P diode cascading region. And upon a combination of these two different transistors cascading with an uniform of this N-type region, leads to a production of the electrical current within stabilized conditions in the case of this JFETs. What is the speciality of this N-channel JFET? We'll be having a detailed look. Considering a transistor which is made up of an N-type material in a P-type substrate, right? In a P-type substrate, N-type metal, that is N-type, and P-type substrate. 3 wires are then connected to the device. Here it is 1, it is 2, and here it is 3. With a soldering, we can connect with respect to these 3 terminals with respect to 3 different wires. One is connected to the substrate, one is connected to the substrate. Likewise, the device bit of PN junction diode, except that there are 2 different wires connected to the N-type substrate. So negative, negative, source, drain, and hence one is gate that is connected to the substrate. And when the electricity or input current has been given to the substrate, P-type substrate, the N-type will execute the current conductions in the following region, and the certain channels has been framed up. We'll be looking in detail that the gate is connected to the source, how the FET is working is done. Gate is connected to the source. Here it is, gate is connected to the source. We all aware of that basic function that PN junction is reverse biased in condition because of this N terminals as a sandwiching between the P-type material. Hence, it is having a little current flow in the gate connection, and the depletion layer also specifies over here. Depletion layer also specifies here how the conduction is being taking place between the N-type and P-type ions. Here, the present N-type channel will be swept away as the depletion layer forms. Hence, the most depleted portion is in the high field between this gate and the drain. Between this gate and the drain is forming at a maximum range between these three regions, resent gate to the drain. Why it is? Because the flow of current along the channel from positive drain to the negative source of really having a free movement of the electrons from the source to the drain in the n-type silicon, and hence it leads to the magnitude of this current will fall more in the silicon and hence become the depleted of free electrons that leads to move or tends to move from this positive is drain to the negative there is source, and hence there is a limit to this drain current that which increases this voltage of drain to source and can drive this channel, and uh, this limiting the current is known as IDSS, that is drain to source current with gate shorted to the source. IDSS stands for drain to source current which the gate shorted to the source. Moving on to the output characteristics of an N-channel JFET, the gate shorted circuit with source. As just we have been passed, have a look at this. There is an initial rise in the input drain current that is related to build up for the depletion layer of the VDS, and the current has been decreased and leads to decreasing in the VD characteristics by increasing the ID. It curve approaches the level of limiting this ID. Yes, that is this gate shorted circuit when ID becomes the pitched off. When this particular ID becomes the pitched off conditions. The physical meaning leads to that pinched off is the value of VDS, which is maximum of IDS flows. So when this physically, when this ID current of this drain has been decreased, or voltage characteristics will be a maximum in the case of this IDSS condition. So, and this IDS condition in the sense the gate shorted circuit with respect to an N channel. So it leads to an saturation region at a maximum level of this IDSS, and it represents with respect to the pinch of voltage, that is pinch of voltage, and hence this VGS leads to the 0 volts. At a static or at a maximum region, it leads to VGS condition leads to 0. Into an conditional strategy with a steady gate source voltage of 1 volts, considering as 1 volts at a source end, the drain voltage of 1 volts means that there will be an 2 volts across the wall and the drain ends, because the drain is up 1 volts from the source, from source to 1 volts from this and the gate is 1 volt down, hence the total difference here it is 2. Here it is the input, that is source, it is 1 volt, and hence having the gate is of 1 volt, and simultaneously from the drain you're considering that overall condition, the total difference between this drain and the source will be of 2 volts. The higher voltage difference at the drain end means the electron channel is squeezed down a bit more at the center. So there will be an voltage and drain with respect to the source, 1 volt drain to the source, and leads to an squeezed down condition, decreased in a strategy a bit more at this particular end drain. Simultaneously, when the drain source voltage is increased to 10 volts, and has been increased to the 10 volts source and the drain in between across this channel, and it leads to the increasing of 11 volts, but it remains 1 volts at the end source. And what about the magnitude or the field that has been generated across the source? The field across the wall near the drain and is now at a larger than at the end of the source. So hence this 11 volts will be as a major factor which will be increasing when this 10 volts has been increased furtherly in between this source and the drain, and consisting of an 11 at this drain, and simultaneously at the source it will be a lot very much less when compared to the drain. And as a result, the channel is very much nearer to the drain. Squeeze it down quite a lot. But next condition, it is increasing the source drain voltage to an 20 volts. Furtherly, the source and the drain voltage has been increased from 10 to 20 volts, squeezes down this ends this channel so very much more. As we increase this voltage, we increase the electrical field within the drive electrons along the open part of the channel, along the open part of this particular channel which has been connected internally. And it also squeezes down the channel near the particular drain also, near this particular drain. This reduces the open channel width and leads to the drain source current, which tends to remain a constant, and we increase the drain source voltage, right? And the major factor or conflict that has been arising in between this source and the drain current incrementing towards the 1 volts to the 10 volts or 5 or nominally 15 or else towards the 20. It leads to the drain source current, which is tends to remain a constant more and increases to a drain source voltage. The reason this functionality is being taking place at a maximum level and leads to a saturation region, that is IDSS current at a maximum of 20 volts of this drain source voltage factors. So this is a pictorial representation how the electrons flow from the source to the drain when the voltage has been applied. And nominally, when this voltage is being simultaneously applied, increasing at the gate level, this particular depletion or gate voltage widens the depletion zones. That is, depletion zones are being increasing furtherly and cutting the term voltage, right? And applying of a small increase in the drain source current, voltage increases. It leads to an increasing of the voltage. The charge carriers are being flown and a large rise is being taking place at the source point, but at the drain it is being decreased. So furtherly, the increasing in the case of this voltage leads to a widening of these charge carriers or exhibitors at the point of the source and large size also. And this is the condition or strategy that the electrons which are flowing from the source to the drain and leads to the incrementing of this particular voltage by widening at this particular source region when the gate and the voltage has been increasing at the gate channel, right? We'll be looking after the point wise and how the current will be getting increased upon the action basis of this particular JFET. Increasing of this VDS increases the width of the depletion layers and furthermorely narrowing at the part of the drain and increasing the depletion constraints at the source point because of the resistance of n channel. This resistance therefore increases with respect to the voltage at the output channel. Hence, the drain current that is being existing, that is IDS is equal to voltage at the drain source by resistance at respect to the AP. And we'll be graphing the current versus the voltage upon incrementing of the current, how the voltage is being just verified in between this drain and the source. And here have this current and voltage exhibits a sublinear behavior because we'll be verifying it with respect to the diagrammatical representation beyond the fact that is the voltage that is being developed due to the incrementing at the drain leads to the generation of this voltage of from source to drain is less than 5 volts. Obviously it's at less than 5 volts, and the pinch off voltage as the magnitude of reverse bias needed is P plus N just touches with the drain end and leads to an actual bias across this pinch across. Here it is the conditions. BP pinch voltage, that is DS at a maximum point of n volts. Beyond this, the channel of electrons movement just you have been seen in the process that is being commencing. When the VDS is increases, most of the additional voltage simply drops across the L, and the region which is a depletion of carriers and hence highly very much resistive. And this voltage drop across this length of the channel, voltage drop of the length of the channel from high to the volts, that is dropping the voltage from the source point to the drain point, is called a pinch, remains as a pinch of voltage. Decreasing is but leads to a pinch of the voltage. So beyond this pinch of voltage, there is ID, which is giving from the drain remains is equal to ID is equal to voltage at a pinch by the resistance of pinch, and hence obviously this VDS will be definitely greater than the pinch voltage, right? Pinch voltage is a factor, and these are the overall drain commencing factors existing in different cases of mass JFETs. All right, we'll be concluding it. This will be concluding today's class, and tomorrow's class will be discussing furtherly towards this transistors concept.